While most of the world's attention has been locked on 3I Atlas, a second object quietly slipped into view just weeks after the interstellar comet made headlines, and for a brief stretch in late 2025, it actually outshined it. This is the story of Comet C 2025 R2, better known as SWAN, and why its sudden appearance sparked a wave of online speculation linking it directly to 3I Atlas. Speculation that, once you look at the actual orbital data, simply doesn't hold up. But the real story here, the one grounded in confirmed observations, is genuinely worth your attention on its own. Let's start with how SWAN was actually found, because it's one of the more unusual discovery stories in recent comet history. On September 11th, 2025, Ukrainian amateur astronomer Vladimir Bezugly was scanning through images from an instrument most people have never heard of, SWAN, short for solar wind anisotropies, mounted aboard the SOHO spacecraft, the Solar and Heliospheric Observatory. SWAN's actual job has nothing to do with hunting comets. It's designed to monitor how solar wind interacts with hydrogen gas throughout the solar system, constantly imaging the sky in ultraviolet light. But because comets release hydrogen as their ice supplements, SWAN has become an accidental comet-finding tool over the years, and this was its 20th confirmed discovery. What Bezugly spotted was strange from the moment it appeared, mostly because of how it appeared. The object was already close to the Sun, just a day away from reaching perihelion, its closest solar approach when it was first detected. It hadn't been caught earlier by any ground-based survey, largely because it spent weeks positioned within about 30 degrees of the Sun in our sky, a blind spot most telescopes simply can't observe due to the Sun's glare. It emerged already surprisingly bright, at roughly magnitude 7.4, with a visible tail stretching about 2 degrees across the sky. Within days, independent observers around the world confirmed the sighting, and it was formally designated C 2025 R2, with SWAN attached in honor of the instrument that caught it. Here's where the timing becomes genuinely interesting, and where the online speculation started. SWAN's perihelion, its closest approach to the Sun, happened on September 12, 2025, at a distance of roughly 75 million kilometers, well inside Earth's own orbital distance. That's a considerably closer solar approach than 3I Atlas ever made, which reached its own perihelion on October 29, 2025, at a much greater distance of roughly 203 million kilometers. Because both objects were making headlines within weeks of each other, and both were technically passing through the inner solar system around the same general period, a wave of online commentary began treating the timing as too coincidental to be natural, suggesting the two objects were somehow connected, coordinated, or even communicating. The actual orbital data tells a very different story. Early tracking of SWAN's trajectory initially left its exact nature uncertain. Because it was discovered so close to perihelion, with only a few days of observations to work with, its calculated orbital eccentricity was extremely close to 1.0, the mathematical boundary between an object that's gravitationally bound to the Sun and one that isn't. For a short window, astronomers genuinely couldn't rule out the possibility that SWAN was itself interstellar. That uncertainty is part of why the two interstellar visitors at once theory briefly had some real traction, before more data resolved the picture. And resolve it did. As more observations came in, including older, previously unnoticed images captured by NASA's Stereo A solar observatory a month before SWAN's official discovery, astronomers refined the orbit considerably. The conclusion: SWAN is not interstellar. It's a long-period comet native to our own solar system, dynamically old, originating from roughly 180 astronomical units out, about 6 times farther than Neptune's orbit, a genuinely distant region of the solar system's outer reaches, but still gravitationally bound to our Sun. That distinction matters enormously. 3I Atlas is a genuine visitor from another star system, passing through once and never returning. SWAN, however exotic its origin point sounds, belongs to our own solar system, and, unlike 3I Atlas, will eventually swing back around on its own long looping orbit. So right from the start, the premise that these two objects are somehow linked, coordinated, or racing towards some shared rendezvous doesn't survive contact with the actual orbital mechanics. They come from completely different places, follow completely different kinds of paths, and their overlapping visibility window in September and October 2025 is best explained by something far less dramatic than coordination. Pure coincidence, in a year that, as it turns out, produced an unusually active lineup of comet discoveries. But don't mistake not connected to 3I Atlas for not interesting, because SWAN's real story, on its own, is genuinely one of the more exciting comet events of the past year. In the next section, we're getting into exactly how bright this thing got, how it briefly became visible to the naked eye when 3I Atlas never did, and why its sudden emergence from the Sun's glare turned it into one of the most photographed comets of 2025. Let's talk about just how bright SWAN actually got, because this is where the real story genuinely earns some hype, no exaggeration required. When Vladimir Bezugli first spotted it on September 11, 2285, SWAN was already sitting at around magnitude 7.4, a full day before its closest approach to the Sun. For context, lower magnitude numbers mean brighter objects, and the general threshold for naked eye visibility under dark skies is around magnitude 6. So even at first detection, SWAN was already knocking on the door of visibility without any optical aid at all. As it rounded perihelion and continued outward through late September, it kept climbing in brightness, peaking at around magnitude 6.0 by late September, and multiple observers reported it holding around magnitude 6 to 6.5 well into October, with a tail that had stretched to roughly 2 degrees across the sky, wide enough to be a genuinely satisfying target for binoculars and long exposure astrophotography. Compare that to 3I Atlas. Despite being the far more scientifically significant object, the interstellar visitor never became visible to the naked eye at any point during its entire passage through the solar system. It remained a target strictly for large telescopes and professional instruments throughout its journey, hovering in the faint end of the magnitude scale that requires serious equipment to even detect, let alone resolve any detail. That's not a knock on 3I Atlas. Interstellar objects, by their nature, tend to be smaller and fainter, especially compared to comets that swing in from much closer regions of our own solar system. But it does mean that for a few weeks in October 2025, if you wanted to actually look up and see a comet with your own eyes, SWAN was the one putting on the show, not 3I Atlas. That contrast produced one of the more remarkable photographs to come out of the entire 2025 comet season. In mid to late October, several astrophotographers managed to capture both objects in the same wide-field frame, SWAN's bright, extended tail dominating the image, with 3I Atlas visible only as a faint, barely their point of light in the corner, distinguishable mainly by its motion against the background stars across multiple exposures. For many observers, that image was likely the only time 3I Atlas was ever captured without the aid of a dedicated telescope, riding along in the same frame as its far brighter, far closer solar system cousin. Now, about the size claim that's been circulating, the idea that SWAN is somehow 100 times larger than 3I Atlas, this is worth addressing directly because it's the kind of number that sounds authoritative but doesn't actually hold up against the published data. What we can say with confidence is that SWAN appeared dramatically brighter and produced a much larger visible tail than 3I Atlas did. But that's a difference in visibility and activity, not necessarily a direct measurement of the size of each object's actual solid nucleus. Brightness and tail length are driven heavily by how close an object gets to the sun, how much ice is sublimating off its surface, and how much dust and gas that process kicks up, not purely by how big the underlying nucleus is. SWAN's perihelion distance of roughly 75 million kilometers is dramatically closer to the Sun than 3I Atlas's 203 million kilometers, meaning SWAN experienced far more intense solar heating, which alone can explain the enormous difference in visible brightness and tail size without needing the nucleus itself to be anywhere near 100 times larger. To date, there isn't a confirmed peer-reviewed nucleus size measurement for SWAN, comparable to the detailed Hubble analysis that eventually nailed down 3I Atlas's diameter at roughly 2.5 to 3 kilometers. SWAN simply hasn't received that same level of dedicated space telescope scrutiny, largely because, as a solar system comet on a long, looping orbit, it doesn't carry the same one-time use-it-or-lose-it urgency that interstellar objects do. So the 100 times bigger framing appears to be conflating visible brightness and tail size, which genuinely were dramatically larger for SWAN with actual physical nucleus size, which remains, honestly, an open question that current data doesn't clearly answer either way. That distinction matters, and I think it's actually more interesting than the inflated number because it gets at something real about how comets work. Two objects can look wildly different in a photograph or a night sky, one blazing with a massive tail, the other barely a smudge in a professional telescope, without that difference telling you much at all about which one is actually larger. It mostly tells you which one got closer to the sun and how much of its surface ice reacted to that heat. What we can say for certain, based on confirmed observational data, is this. SWAN put on a genuinely striking naked eye show through late September and October 2025, briefly becoming one of the most photographed comets of the year, while 3I Atlas, despite being scientifically far more significant as only the third confirmed interstellar object in history, remained invisible without serious equipment throughout its entire passage. Both are real, both are worth understanding, but they are two completely unrelated objects that simply happen to share a season in our sky. In the next section, We're getting into where SWAN actually came from, what its unusual distant origin point tells astronomers about the far outer reaches of our own solar system, and why, despite not being interstellar, its discovery still matters scientifically in its own right. Let's dig into where SWAN actually came from, because even though it isn't interstellar, its true origin point is genuinely one of the more scientifically interesting parts of this story, and it deserves more attention than it's gotten. When astronomers first tried to calculate SWAN's orbit, they ran into a real problem. It was discovered just a single day before reaching perihelion, which meant they had very little observational baseline to work with. Orbital calculations for comets get more precise the longer you can track an object's motion against the background stars. And with barely 24 hours of data before the comet was already swinging past the sun, the uncertainty in that first orbital solution was substantial. That's exactly why, for a short window in mid-September 2025, the possibility that SWAN might be interstellar wasn't dismissed outright by the scientific community. The calculated eccentricity sat right at that critical boundary near 1.0, and depending on which data points were weighted most heavily, early solutions ranged from slightly hyperbolic, meaning not bound to the sun, to a very long elongated ellipse, meaning bound, but on an extraordinarily wide loop. That uncertainty resolved fairly quickly, though, once researchers did something clever. They went back through archived data from instruments that hadn't been looking for SWAN specifically, but happened to have caught it anyway. NASA's Stereo A Solar Observatory, a spacecraft primarily used to study solar activity, had unknowingly captured images of the object about a month before its official September 11th discovery. Finding those pre-discovery images gave astronomers a much longer observational baseline to work with, stretching the tracking window back to early August 2025. And that additional month of data was enough to nail down the true orbit with far more confidence. The refined answer: SWAN is dynamically old and originates from an extraordinarily distant point in our own solar system, roughly 180 astronomical units out, which is about 6 times farther from the Sun than Neptune's orbit. To put that in perspective, Neptune, the outermost recognized planet, orbits at roughly 30 astronomical units. SWAN's aphelion, its farthest point from the Sun, sits so far beyond that boundary that it's genuinely difficult to picture on a normal scale. That distance places its origin in the sparse, frigid outer reaches of the solar system, in the transitional zone between where the classical planets end and where the vast, distant Oort cloud is believed to begin, though technically not quite far enough out to be considered a true Oort cloud object in the strictest sense used by researchers. Why does that matter scientifically? Because every comet we catch from this kind of extreme distance is effectively a message from the deep freezer of our own solar system, material that's been sitting largely undisturbed at temperatures barely above absolute zero since the earliest days of planetary formation over 4.5 billion years ago. Unlike short-period comets that swing past the sun repeatedly and gradually lose their more volatile ices with each pass, an object like SWAN, making what may be one of its first and close approaches to the sun in a very long time or possibly ever, gives astronomers a genuinely pristine sample of primordial solar system material to study. That's also part of why SWAN reacted so dramatically once it got close to the sun. Material that's spent the vast majority of its existence at extreme distances, barely warmed at all, tends to be rich in highly volatile ices, the kind that sublimate rapidly and dramatically the moment they're finally exposed to real solar heating. That's a large part of the explanation for why SWAN brightened so quickly and produced such an extensive, visually striking tail relative to its likely modest nucleus size. It wasn't a matter of the object being unusually massive. It was a matter of pristine, highly reactive material meeting real sunlight for what may have been the first time in an extraordinarily long time. This is also a good moment to address the online narrative directly. The idea that SWAN's timing alongside 3I Atlas, its sudden emergence from the sun's glare, and its dramatic brightening somehow point to something coordinated or engineered. None of the confirmed orbital or spectroscopic data supports that. SWAN's trajectory is fully consistent with a natural long-period comet, responding predictably to solar heating as it approaches perihelion. There's no evidence in any published tracking data of unexplained course changes, no confirmed detection of anomalous energy output, and no legitimate scientific source reporting the kind of controlled propulsion or plasma shield behavior that circulated in some corners of the internet during its most visible weeks. What actually happened is straightforward, if genuinely exciting on its own terms. A distant, ancient chunk of primordial solar system ice, likely making one of its first real passes near the sun, got caught on camera by an instrument that wasn't even designed to look for it, and put on a brief striking show before continuing on its long, looping path back out into the depths of the outer solar system. And that's really the heart of what makes this story worth telling, honestly, without needing to dress it up. Two genuinely remarkable objects happened to share our sky during the same few weeks of 2025. One, a true visitor from another star system, ancient beyond easy comprehension, carrying chemistry unlike anything native to our solar neighborhood. The other, a native resident of our own solar system's farthest, coldest reaches, offering its own kind of ancient, pristine window into the earliest material that helped build the world we live on. Neither needs the other to be interesting. Neither needs an invented connection to justify your attention. In the final section, we're going to look at where SWAN is headed now, what its confirmed orbital period tells us about when, if ever, it might return, and what this entire overlapping season of comet discoveries actually tells us about how much more active our sky has become now that we finally have the instruments capable of catching events like this. So let's bring this all together, because between two genuinely remarkable comets sharing the same stretch of sky in late 2025, there's a real story here, and it doesn't need any invented energy readings or ancient prophecy to be worth your attention. Here's where things actually stand, based on the confirmed published data. C2025R2, known as SWAN, is a real, verified long period. Comet native to our own solar system, not an interstellar visitor, and not connected in any physical way to 3I Atlas beyond sharing. A few overlapping weeks of visibility in our sky during September and October 2025. It was discovered somewhat by accident, spotted by an amateur astronomer combing through images from an instrument built to study solar wind, not comets. It reached perihelion on September 12, 2025, at a distance of roughly 75 million kilometers from the Sun, considerably closer than 3I Atlas's own perihelion of 203 million kilometers on October 29th. And it briefly became one of the most photographed comets of the year, peaking at around magnitude 6, genuinely visible to the naked eye under dark skies, something 3I Atlas never achieved throughout its entire passage through our solar system. As for where SWAN actually came from, refined orbital calculations, made possible by unexpectedly finding pre-discovery images, captured a month earlier by NASA's Stereo A solar observatory, confirmed it originates from roughly 180 astronomical units out, about 6 times farther than Neptune's orbit. That places it among the more distant, dynamically old comets discovered in recent years, likely making one of its first real close approaches to the Sun after an extraordinarily long journey through the solar system's coldest, most remote regions. Because comets on orbits this large and this eccentric take an enormous amount of time to complete a single loop, often many thousands of years, SWAN isn't the kind of object anyone alive today will see return. Its current trajectory is now carrying it back outward, away from the Sun and Earth, on a path that will keep it in the deep, frozen outskirts of the solar system for a very long time before, if ever, it makes its way back this way again. Now let's address the elephant in the room directly, one more time, because it's worth being completely clear about it. The idea that SWAN and 3I Atlas are connected, coordinated, or represent some kind of sequential contact event doesn't hold up against any of the actual tracking, spectroscopic, or orbital data published by NASA, ESA, or independent research teams. SWAN is bound to our Sun. 3I Atlas is not. They originated from completely different regions, entered our solar system on completely unrelated trajectories, and their overlapping visibility window is best explained by something far less dramatic than a hidden pattern. 2025 simply turned out to be an unusually active year for comet discoveries, partly thanks to instruments like SOHO's SWAN camera and NASA's Atlas survey, both operating at a level of sensitivity that's increasingly good at catching objects that would have gone completely unnoticed a decade or two ago. And that, honestly, might be the most genuinely exciting part of this whole story, more than any invented power core or ancient warning ever could be. We are, right now, in the middle of a real, measurable increase in how many of these objects we're catching. 3I Atlas, only the third confirmed interstellar object in recorded history, was found using a survey system built to protect us from asteroid impacts. SWAN was found by an instrument designed to study solar wind, not comets at all, using a discovery method that's become almost accidental. With the Vera C. Rubin Observatory in Chile now conducting full, dedicated sky surveys as of 2025, specifically built to catch faint, fast-moving objects far earlier than previous systems could, researchers across the field expect the coming years to bring a genuine wave of new comet and interstellar object discoveries, possibly at a pace we've never experienced before. So here's the real takeaway from this entire story, and it's one that doesn't need any exaggeration to land. We just lived through a season where two genuinely different, genuinely remarkable travelers, one from the ancient frozen edge of our own solar system, one from another star entirely, happened to share our sky within weeks of each other. One offered us a rare, direct, naked-eye connection to the oldest material our own solar system has to offer. The other gave us a fleeting, telescope-only glimpse of a wanderer that may be older than the sun itself, here for the first and only time in its multi-billion-year existence. Neither needed to be secretly connected to the other to matter. They were each, on their own, exactly the kind of event that reminds you how much is actually moving through the space around us, largely unnoticed, until the right instrument happens to be looking in the right direction at the right moment. So here's the question worth carrying away from this one. With detection technology improving this quickly, and two major comets, discoveries landing in the same few months of a single year, what do you think we're going to catch next? And will it be another quiet solar system wanderer, or the fourth confirmed visitor from another star entirely? If this breakdown helped you separate what's actually confirmed about Comet SWAN from what was just online speculation tying it to 3i Atlas, hit that like button. Subscribe if you're new here, and let me know in the comments which of these two comets you found more fascinating. Because if this year is any indication, we're not going to have to wait long before the next one shows up.